So finding trig values, missing sides, and missing angles. So we're going to put the trig definitions to use, which we introduced in a previous video. So we have 6 trig functions for a specific angle theta, which is going to represent an acute angle on our right triangles for now. So here are the 6 trig functions. We have sine, cosine, and tangent, cosecant, secant, and cotangent. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Cosecant is the reciprocal of sine, hypotenuse over opposite, hypotenuse over adjacent, and adjacent over opposite for secant and cotangent, respectively. Now, the common acronym that high school students often refer to with trig definitions is what is called, or what is named, SOHCAHTOA. So if you've heard SOHCAHTOA before, it reveals the trig definitions for sine, cosine, and tangent, which are the 3 that we are going to primarily use and resort to when finding missing sides and angles. So although you can use the other 3, they are less common. And at this point in your math career, we're going to stick with these 3 for finding missing sides and angles. So how do you use SOHCAHTOA to your advantage? Well, first you need to make sure you spell it correctly. But the S, the C, and the T represent sine, cosine, and tangent. And then the 2 letters thereafter tell you the ratios of the side lengths for their definition. So opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. So if you remember SOHCAHTOA, you know the trig definitions for those primary 3 that we are going to use. So now, what types of problems are we going to be looking at? Let's say we're given a right triangle, and we have some angle theta, and we have the side relationships of 3, 4, and we need to figure out the values of the 6 trig functions for theta. So sine of theta, we know is opposite over hypotenuse. We don't have a hypotenuse right now. Well, we know how to find a third side on a right triangle in the event that we have 2 of them. That is through Pythagorean theorem, and we would find out that the side is 5. So if you come across a problem that you're missing a side that you need in order to find the value of one of these trig functions, if you have 2 of them, use Pythagorean theorem to get that third. So sine is opposite, which is the value of 3, and hypotenuse, which is the value of 5, and that ratio gives us the sine. So recall that when we refer to opposite, adjacent, hypotenuse, that's all in reference to a specific angle. So the opposite is the leg directly across from theta. The adjacent is the leg that is adjacent to theta, or next to, obviously is adjacent if that's the name. And then hypotenuse is the longest side. So there we go. So for some students, it is helpful to label opposite, adjacent, and hypotenuse for that particular angle before they begin. And again, if we introduce another acute angle and I asked you for the sine of alpha, well then the opposite changes in relation to alpha, or sorry, when compared to theta, I should say. So this is our opposite for alpha. So the sine of alpha is going to be 4/5. And you can see that the value of the trig functions changes depending on the value of the angle, okay? So very important to understand. So let's go back to theta. What's my cosine? It's going to be adjacent, which is 4 over hypotenuse 5. What's my tangent? It's going to be opposite over adjacent. And by the way, these are the answers. So if I ask you for the trig value, so if I say, what is sine of theta? All you have to do is give me 3/5. That's the answer. Okay? It is, so trig functions are defined as ratios of side lengths. You should get some constant value by taking one side length and dividing it by another. And if I want the other 3, all I have to do is take the reciprocals of these ratios here. Okay? So now that we understand how to find trig values, all you have to do is write ratios of side lengths for that particular angle. Make sure you identify opposite, adjacent, and hypotenuse correctly. How do we leverage these definitions in order to find missing sides or missing angles? Well, the cool thing about the trig functions that is going to open up some new opportunities for us is when we were trying to find missing sides or for right triangles, we were limited into what types of triangles and what information was needed in order to solve the problem. For a right triangle, to find a missing side, we needed two sides at the very least for the utilization of Pythagorean theorem, or if we had a special right triangle scenario, whether it's a 45, 45, 90 or a 30, 60, 90, we were able to find a missing side with only one side length. But now that we have trig definitions, we will be able to find a missing side with only one side as long as we're given one of the acute angles. So let's introduce this acute angle to be, say, 60 degrees. Actually, let's do a non-right triangle. So 65 degrees, say. And they want us to find, say, this missing side, x. So again, we don't have a special right triangle situation here, and we don't have two of the sides, so I won't be able to do Pythagorean theorem. So what can we do? We're going to stick to those primary three. We're going to write SOHCAHTOA off to the side. And here's how you find a missing side using trig. Look at the angle that is given, and then label the sides that you have in this problem in relation to that angle. So I would say 3 is the opposite side in relation to 65, and x, the one I'm looking for, is the adjacent side. So you label those two sides, and then you identify which of the three trig functions works with opposite and adjacent. And we would see that that is tangent. Once I know that I'm going to use tangent, I write the definition for tangent of an angle. This definition is an equation that I will be able to solve. I fill in what values I have for the three variables present in this equation. The three variables are the angle, the opposite side, and the adjacent side. I have an angle measure, 65 degrees. I have an opposite side, and I'm looking for the adjacent side. Now I have an equation that I can solve for this variable x. I would move x to the other side because it's in a denominator by multiplying. Then I would divide by tangent of 65. So a common mistake is that people might move the 65 independently. But all the trig functions, when written, need to be accompanied by an angle measure. So this thing needs to be moved as a whole piece. So I can't move just tangent without anything with it, and I can't break off the 65, right? So whenever I write a trig function, make sure it's accompanied with an angle. So I'm going to divide both sides by tangent of 65. And we're going to use our calculator to make this computation, but if we didn't have one, we can leave our answer like this. So in this calculation for the calculator, whatever number is revealed, that will tell you the length of that side. So pretty cool. Okay? Now, what if I wanted to find the length of the hypotenuse instead, and I still have the same situation? We'll label the sides according to the angle that's given. So we have opposite and hypotenuse. And then I'm not going to use tangent this time. I'm going to say, well, which of the three trig functions of these primary three work with opposite and hypotenuse? So this time I'm going to use sine. I'm going to say the definition is as follows. Fill in the variable values that you have and keep the one you're looking for as a variable. So we have 65 for the angle. We know the opposite. We're looking for the hypotenuse. Using that same process as before, if x is already in the numerator, it's an easy calculation. We just multiply by the value of the denominator. But if it's in the denominator, we want to move it. And then we're going to divide by sine of 65. So we're going to get x equals 3 over sine 65. And whatever value we get from the calculator will tell us how long the hypotenuse is when the angle is 65 and the opposite side is 3. If we start changing the angle or the opposite side, we're obviously going to change the length of the hypotenuse, and this calculation would change as a result. But the point is, when we're trying to find a missing side, label the sides, then identify what trig function to use. And we're using the trig definitions to answer these questions because the trig definitions are equations and they have variables in them. We plug in the values for those variables that are given to us in the problem, and we solve for the missing piece. So now we know how to find missing sides using trig. How do we find missing angles? So let's say that this hypotenuse is 6. And we want to know what is the angle for theta up here. So what is the measure of that angle in the event that that adjacent leg is 3 and the hypotenuse is 6? Well, how you start these problems the exact same as the missing sides. We're still using trig definitions. We want to label the sides according to the angle that we're looking for. So we have adjacent hypotenuse. And when we label that, that's going to dictate what trig function to use. So we know adjacent hypotenuse is going to be dealing with cosine. So we're going to write our cosine definition. We're going to fill in what we have. The thing that's missing is the angle. So we leave that as a variable. And we have 3 over 6. Now, how do we solve for the angle theta? We want to isolate theta and get a measurement. So we have to be able to move this cosine. But we said that whenever we write a trig function, it has to be accompanied by some angle measurement. So I can't do this. Super common mistake when finding an angle. I can't divide by cosine because what are you going to plug in to a calculator? It's the cosine of what? They're going to be like, well, what are you taking the cosine of? So I can't just move COS because this is not multiplication. It's the cosine of something. Now to solve this, we're still going to use the same algebraic principles that we always use to solve equations. So if I take some linear equation, x plus 4 equals 5, and I want to solve this, to move the 4 to the other side, I subtract 4. Why do we do that? Because addition and subtraction are inverse operations, and that will allow them to cancel out. So what I need to be thinking of is, what is the inverse operation for the cosine of an angle? That's how I would cancel it out and isolate theta. The answer is you take what's called the inverse cosine of both sides. And the notation for that is you put a little -1 in kind of like an exponent position. And we're going to do that on both sides, right? Whatever we do to one side, we do to the other to keep the equation balanced. And what you'll see is we said the trig function should be accompanied with some value, right? They shouldn't be standalone letters. There should be a number associated with it. So this equals some value that we're going to put in parentheses there. And we have this number. So what happens on the left is taking the inverse cosine of a cosine cancels this out because they're inverse operators and it isolates theta. And then we have cosine inverse, or the inverse cosine of 3/6. And there is a button on the calculator to allow us to calculate this. If we didn't, we could leave our answer like that, and that will get us the angle measurement for theta. So we're going to summarize that inverse idea. So let's say I have sine of theta equals opposite over hypotenuse. We have cosine of theta equals adjacent over hypotenuse. And we have tangent of theta is equal to opposite over adjacent. And you want to figure out the angle for whatever trig function you ultimately have to use for a specific problem. So again, what trig function you use is going to be dependent on the information given in the problem. But to isolate theta, we're going to incorporate inverse trig. So we're going to take up top the inverse sine of both sides. So what's going to happen on the left, if I take the inverse sine of sine theta, it cancels, I get this. But I also must take the inverse sine of the other side. So to find the angle, I'm going to do inverse sine of the ratio opposite over hypotenuse. We already saw the results for the cosine. We're going to do inverse cosine of the ratio for the adjacent to the hypotenuse. And then lastly, to get the angle when I have a tangent scenario, as you could guess, I'm going to do inverse tangent of opposite over adjacent. So to isolate an angle, we must use the inverse trig. That is unnecessary when finding a side. We can just use basic inverse arithmetic applications, whether it be multiplication or division, which is primarily what you're going to use. And that's that. So that's how you find trig values, given sides for a specific angle, how you find missing sides and how you find missing angles, all of which are found utilizing the trig definitions. The trig definitions are themselves an equation. We plug in what we have and solve for what we're looking for.